Hi, good morning everybody, and welcome to this morning's webinar from PILT, finding the right safety locking device. My name is Jason Reed. I'm your presenter today. I'm one of the account managers at PILT. You can type your questions using the toolbar to the right hand side of your screen, and my co-hosts, who are Tony Matton and Jamie Thomas, will do their best to answer any questions you have during the course of the webinar. If we can't, then we'll come back to you as soon as we can afterwards. The webinar is being recorded, and a link to the recording will be sent out to everybody that's registered shortly afterwards. A copy of the webinar slides are available on request, so just use the toolbar on the right-hand side to request those. So the agenda for today, we'll look at a quick structure of standards. We'll do an introduction and the structure of 14119 for interlocking. We'll then look at finding the right safety interlocking device. We'll cover fault masking. We'll look at manipulation to defeat. And then it's not just about the interlock. We'll also look at 13849. And then we'll finish off really with some new products from PILT for guard locking that are coming out later on in 2024. And then finally, we'll just finish with future webinars. So standards. So a recap really of the structure of standards. They're broken down into three tiers really. So we have A standards, of which there's only one, which is ISO 12100 for safety of machinery, general principles for design, risk assessment and risk reduction. We then have B standards, and these deal with certain machinery safety issues or certain types of safeguards. So 14119 or 13849, for instance. And then we have C standards that contain specifications for certain individual machine groups. So EN 415 for packaging machines, for instance. So in line with 12100, if the risk has not been adequately reduced, then we look at risk reduction by protective measures. So first we look at inherently safe design measures. So can we change the way that something is operated, like a chain and pulley? Could it be a belt mechanism, for instance? Then we have safeguarding and complementary measures, and this is where 14119 and interlocks would come in. And then we have information for use. If a protective measure is dependent on a control system, such as interlocking, then we'd look at either 13849 or 62061 to see how we would design that. And for the purpose of this webinar, we'll really focus predominantly on 13849. So safeguarding, some standards to consider. So we need to look at 14120, which is general requirements for design and construction of fixed and movable guards. We need to look at 13857 for safety distances to prevent hazardous zones being reached by upper and lower limbs. 13855, position of safeguards with respect to approach speeds. And then I've got 14119 for interlocking devices associated with guards. So a safeguard is either a guard or a protective device, and a guard is part of the machinery used specifically to provide protection by means of a physical barrier. And a protective device is a device other than a guard which can reduce the risk either alone or in conjunction with a guard. An example of that would be a manufacturing cell that you see here. You've got perimeter guarding, and then you've got a number of other safeguards around it, such as interlocks, light curtain scanners, radar, etc. So 14119. Presumption of conformity to the machinery directive came out or came into effect in 2015, and in the UK this would now be the Supply Machinery Safety Regulations 2008. This standard is relevant to anyone that manufactures interlocking devices or uses interlocking devices. So that covers OEMs such as PILTs, OEMs of machines, and end users alike. So how does how is the standard structured really? So we have the scope. So this is what really it covers. Normative references. So this makes reference to other standards such as 13849, 13857, 14120. We have terms and definitions, and this is a glossary really of for instance, what is guard locking. We have operating principles and typical forms of interlocking devices associated with guards, and we'll look at that in a bit more detail. We have the requirements for design and the installation of interlocking devices with and without guard locking. It covers fastenings, switch and actuators, actuation mode, how does it interface to a control system, etc. Clause 6 is the selection of an interlocking device. 7, designed to minimize defeat. Clause 8 will be control devices. So that's looking at common cause failure, fault exclusion, and we'll be looking at those in a bit more detail. And then finally 9 is information for use, which again, that could be given by the manufacturer of the interlock, such as PILT, or by the manufacturer of the machine. And then finally, towards the end, you have all your informative annexes, really, that will give you examples. So finding the right safety locking device. So when selecting an interlocking device for a machine, it's necessary to consider all phases of the machine life cycle, and selection shall take into account, but not be limited to, the following criteria. And that's the conditions of use and the intended use of the machine, the hazards present at the machine, the severity of possible injury, the probability of failure of the interlocking device, overall stopping performance and access time, the required performance level or safety integrity level, and for type 4 interlocking devices, the means to avoid that a single actuator can be taught in an unlimited manner by the operator without specialist knowledge or at all. And so types of interlocking devices according to 14119. So the actuation is broken down into two types, mechanical and non-contact. And then for mechanical, you have cam or hinged, or they could be tongue-shaped actuators or trap key interlocks. And then for non-contact, you have inductive, capacitive, optic, magnetic, and RFID. The difference between those then is then the uncoding or the coded part, and then they're broken down into types, either type 1 for cam or hinged, type 2 for tongue-shaped actuators and trapped key, type 3 for inductive, capacitive, and optic, and type 4 for magnetic and RFID. What we mean by the coding is low-level coding for which there's not for which there would be 1 to 9 variations in code are available. Medium level, 10 to 1,000 variations in code, and high level where there's more than 1,000 variations of code. And high level covers uniquely coded RFID systems. Medium typically covers trap key systems and some limited RFID systems. And low covers magnetic reed switch types and reteachable RFID type. And then so just some examples really. So, you know, a hinge switch, trap key or tongue actuator, interlock, inductive, and then we've got some RFID coded switches. So selection of guard locking devices. So this is the table that's taken out of 14119. So we start, what's the overall stopping performance against the access time? So if the stopping time of the machine is less than the access time, then we can use an interlocking guard without guard locking, and that can be sufficient. And we can also refer to 13855 to look at the stopping time required. If the stopping time of the machine is greater than the access time, then we'd need to use an interlocking guard with guard locking. So interlocking devices in more detail. An interlocking device are used in conjunction with movable guards, and together they ensure that the following functions are performed. The guard remains closed and locked until the risk due to the hazardous machine movements have disappeared. The hazardous machine functions occurred by the guard cannot operate until the guard is closed, and if the guard is opened while the hazardous machine functions are operating, a stop command is given. And when the guard is closed, the hazardous machine functions covered by the machine can operate, but the closure of the guard does not in itself start the hazardous machine functions. We then have guard locking devices. So interlocking guards can also be provided with these guard locking devices to ensure that the guard remains closed and locked until the risk due to the hazardous machine movements has disappeared, and the hazardous machine functions cannot operate until the guard is closed and locked, and when the guard is closed, the hazardous machine functions cannot start on closure of the guard itself. So a general note then is when interlocking with guard locking is applied, opening of the guard shall be prevented by a guard locking device unless all hazardous machine functions associated with the guard have ceased. And there are two alternative designs for the guard locking function. So you've got unlocking of the guard can be initiated at any time by the operator. When the unlocking is started, the guard locking device generates a stop command. This is called unconditional locking. The time necessary for the guard to be unlocked shall be greater than the time necessary for the hazardous machine functions to cease. And then we have unlocking of the guard is only possible when the hazardous machine functions have ceased or hazardous situations have ceased. And this is called conditional locking or unlocking. And a chart that we have that my colleagues in Germany have put together for us is a quick way of being able to really select the interlock from PILTs, the guard locking device from PILTs that would be required for your application. And so we can start with the guard type. Is that a safety gate, a cover, a flap, or is it a swing gate or a sliding door? Is it part body access? So what we mean by that is it just a cover or a flap, so you can just open the cover and put your arm in, for instance, or is it whole body access, like a gate, so you can physically walk inside? And then based on that, it would be whether or not for part body access, whether it's process guarding. So the intervention time, the time to gain access, is greater than machine rundown time, or for process guard locking, is the intervention time less than the machine stopping time. You then have to calculate your performance level required, and then that would give you the correct guard locking device to use. So for process guarding, what's possible is your machine could be running, and then if you wanted to, you could unlock the guard locking function of that part. So let's say it's a cover or a flap. You've got a standard interlock on there, and anybody can open that flap at any time. The machine would stop safely because your intervention time is greater than the machine stopping time. However, you want to prevent that from happening. So you could put a guard locking device on there. However, in this instance, it's still possible to unlock the guard locking function if required, so that you could still monitor a process from the outside, and then you could open the gate or the flap in this case, and that would then stop the machine. The alternative with a process guard locking device is that you actually want to protect the process completely. So you don't want anybody to open that flap or that cover unless the process allows it. And so in that case, you would request to enter, and then when the machine comes to a stop, it would then allow you to release the guard locking function and gain access. The alternative is for whole body access. We have process guarding, so that's the same, but then we use safeguard locking in that instance because we're saying there's whole body access and we want to protect the person from an expected startup, for instance. And so in that case, you would want to ensure that the process is stopped completely, and you would use slightly different devices from PILTs to allow for the unprevented startup. So an example of that for a guard locking device for process locking would be the application here with flaps, and we have our PCM mech 1 device, which is possible for this, or 5, and this allows for guard locking via spring force and a magnetic force. We have an auxiliary release with a spring force, and there is an escape release and emergency release possible. So what we mean by that is an emergency release means that you could gain access into the machine if there was no power. An escape release would mean that if you had gained access and you were locked in, then you can escape out. And then for this particular device, we've got 5 different actuation positions that can be used. Holding force of 1500 Newton meters, for example. If we now looked at whole body access that was discussed earlier, then here's the application, here's our robot cell. We want to ensure that this process has come to a stop, or the robot has come to a stop before we gain access, so we'd request to enter. When it was safe to do so, then that would allow for the guard unlocking. The person would then enter, and then when they finished, they would come on out and reset the machine. So an example of that would be our S-lock that's showing here. Our M-lock that's showing here. This meets all the requirements of 14119 up to PLE C3, and we do various versions of this with and without series connection. Again, with or without what's called a power reset. I can run through that later on. And we can also use this with our PIC gatebox reader to allow that only trained, authorized and competent people can gain access. So we now cover fault masking for series connected machines. So clause 8.6, logical series connection of interlocking devices. So logical series of connection of interlocking devices means that for normally closed contacts while in series, or for normally open contacts while in parallel, when interlocking devices with redundant contacts are logically connected in series, the detection of a single fault can be masked by the actuation of any interlocking device logically connected in series with a defective interlocking device to the safety-related control system. And it's therefore foreseeable that during the fault finding process, i.e. the troubleshooting process by an operator, one of the guards whose interlocking devices are logically connected in series with the defective interlocking device will be actuated. And in that case, the fault will be masked and the effect on the diagnostics coverage value shall be considered. And we have a technical report 24119 that deals with logical series connection of devices. And what that will do is that is a technical report that is dealing or detailing a specific case on how to deal with serial connection of interlocking devices, and that the influence on the diagnostics capabilities of the safety interface. And as there's a number of machines out there that have been in service for a number of years, it's worth considering fault masking for these and for new machines. So TR24119 has a simple method really to look at maximum diagnostics coverage, and it's made up of 3 columns. So we have a number of frequently used move guards, number of additional movable guards. We have maximum achievable diagnostics coverage. And by frequently, we mean it's opened at least it's open at least once every hour. But as soon as you have 2 switches in series, then the maximum diagnostics coverage you can achieve for that is medium. And in any case, if multiple movable guards will be open at the same time as part of a normal operation or maintenance, let's say, or service, to clean the machine at the end of a production run, then it's foreseeable that the fault masking will occur. So if you've got a machine with 3 doors, 3 covers, for instance, and it's foreseeable that those would all be open at any one time, then it's foreseeable that obviously the fault masking would occur then. And what do we mean by fault masking? So in this example, we've got 3 gates. They're all wired in series back to a safety relay. And let's say for this example that it's in a food production environment, and they have an end of shift washdown. So as it stands at present, all the guards are closed and the safety relay sees no issue and the machine is running. For some reason, the operator needs to open the guard, and in this case, it's guard number 1. It could be due to a batch misalignment, let's say. And when they open guard 1, channel 1 opens, but channel 2 is defective, and that remains closed. The safety controller switch is off, and it stops the machine. And at present, the machine is in a safe state. Once they've cleared the misalignment, the operator then closes the guard, but channel 2 is defective. The safety controller does its job and it detects that fault and it prevents the machine from being reset. And again, the machine at present is still in a safe state. So either due to time pressure or the operator knowing how to overcome this issue for guard number 1, they go and open guard number 3. And when they do that, channels 1 and 2 both open, which is what the safety relay is looking for. And it thinks now that that fault is cleared. The machine at this moment in time is still not in operation. So guard 3 is now closed. However, the channel 2 fault on guard number 1 is now masked. The safety controller is enabled and the machine can be started with that masked fault. Now over time, it could be due to the machine being washed out, etc. Channel 1 on guard 1 also fails. So this could be down to water ingress, for instance. The safety controller is enabled and the machine can now be started with a fully dysfunctional interlock. So when guard 1 is opened, the safety controller does not recognize the guard state, and due to the failure in the 2 channels, the contacts remain closed and the machine continues to run with the guard open. So this is a complete loss of the safety function. So how do we overcome fault masking? So we can, or we could, individually wire interlocks and other fault-free devices, such as e-stops, directly back to individually safety relays or to modular safety relays, and we could create hardwired logic without software between the safety relays as required. And if need be, we can tie them together, and we can use that using our Pilt Sigma or MyPNOS non-software based safety relays, or we can wire them individually back to a software configurable safety controller with multiple inputs, such as our MB1 and MB2 controllers. We can also wire guards or zones as below using a PDP-20 module, which has test pulse outputs. So this avoids the need to rip out any existing switches, fault-free switches, by monitoring the existing switches individually via a 4-way gang array, and that links back to one safety relay. So this kind of minimizes changes to switches on site, reduces your costs of cabling, and it can improve the safety potentially up to PLE per switch. So the OSSDs are an output signal switching device, and they look like a safety relay, but they have 8 input channel units that monitor up to 4 switches, And as long as all channels are healthy, it gives you an output that can be wired to other PDP-20 monitoring devices, and they then go back to the safety relay. So instead of removing your existing fault-free switches, you can add these PDP-20 units to your machine, which would obviously minimize the changing of the switches, reduce cost of cabling, improve your safety up to PLE per switch, because you could claim 99% diagnostics coverage. So we'll just give an example of that now. So this is our machine X1. It's looking at 4 individual switches to make sure that they are healthy, and the output is going to X2, which then has 3 switches wired into it. The output, which is OSSD, is then going into the safety relay, which is then used to control the main access to the machine. They can be used for all fault-free switches, such as interlocks, e-stops, and this is an example of how it would be wired. They have a very high input impedance, which means that PDP-20 units can be cascaded over hundreds of meters on or within a panel as a digital input expansion. So if a series of interlock switches is required to meet PLE, using switches with integrated fault detection can overcome fault masking. So interlocking devices that feature OSSDs with microsecond off-pulse fault detection and inputs with plausibility cross-checking built in are unaffected by fault masking. Though this isn't necessarily for guard locking, the devices that we use for guard locking will use this technology as part of the interlocking part function. So effectively what's happening is the switch to the left is basically checking the output of the switch to the right. And it's a RFID frequency, so there's no internal moving parts. So it could be IP67, IP66. That could be achieved. Then you could have temperatures from -25 up to +70. It comes in different shapes and sizes depending on the application, and the actuator can be mounted in various positions. And we also, well, for interlocking, we've also released the smallest profile actuator that you can use, which can be a DZIF, used with a DZIF to locate it onto the machine, and then if it's peeled off, it destroys that RFID actuator. So if each safety switch, so if we're wiring it that way, we have to bear in mind that each safety switch has an intrinsic reaction time or risk time, and for PILTs that maximum is 260 milliseconds. So each safety switch also has a delay on de-energization time or propagation time to process the incoming ESDs from the previous switch, and from PILTs that maximum is 20 milliseconds. So the function of the furthest away switch has a resulting reaction time equal to its own intrinsic reaction time plus the sum of all the propagation times of all the switches and the safety relay downstream. So an example of that would be our 4 guards that we saw on the previous slide. So we've got our 4 guards, our 4 switches. If we look at switch number 4, that has a reaction time to switch. Plus we then have to look at the 4 switches as well, and the reaction time of the safety controller. So in this example, it would be 260 milliseconds for the first switch, 3 times 20 milliseconds for the remaining 3 interlocks, and then it would be 20 milliseconds for the safety relay. So we have a total time of 340 milliseconds, and that needs to be considered for the safe distance between the end guard for interlock and the hazard stopping time. And again, we can use our stop performance calculation for this from 13855. We can also look at distributed fail-safe inputs. So you can distribute fail-safe inputs into a safety relay via a passive IP67 rated input modules, and we do this with the PILT PDP 60 up with a PDP 67 unit, and that operates with an 8-pin OSSD based architecture. So you can use switches such as our magnetic PSEN S2 into a guard locking interlock. We then have distributed fail-safe inputs into programmable safety relays via our IP67 input modules. So we have our PDP 67, which can be used for all safety sensor types that are contact based or OSSD based. And this is connected to a programmable safety relay, such as our PNOS Multi 2. And these PDP 67 modules can be used with all safety sensors. And the PNOS Multi using IONet modules, and the benefit of this really is you've got a high level of safety up to PLE SEAL 3. You can use it for long cable runs up to 1,000 meters. You're reducing your field cabling and panel space. You can reduce your installation time and therefore costs. You've got local diagnostics via local LEDs, rapid commissioning, etc., and future expansion of your machines. So an example would be a PNOS multi-based unit with 4 PDP link modules, then up to 4 PDP 67 field blocks could be used per link module, and you can have up to 4 dual channel units per PDP 67 field block. So potentially you could have 64 dual channel sensors connected, and where voltage drops occur, we can provide the PDP 67 field block with an additional power source. So let's look at motivation to defeat. So why do we need to look at this? Well, some may have seen this. A report was carried out via our German colleagues, and its findings were that 37% of safeguards are manipulated either constantly or occasionally, and that 25% of all accidents when operating machinery can be attributed to manipulation. So a quarter of all machinery operating accidents were caused by manipulation. And 14119 states that the machine shall be designed in such a way that it minimizes the motivation for defeating the interlocking device, and that the interlocking device shall provide minimal possible interference with the activities during the operation and other phases of the machine life cycle. And we use the following procedures in order to avoid interlocking devices being defeated. And again, this kind of chart is taken out of 14119. So we look at implementing basic measures. Is there then a motivation to defeat? If not, we can end. If there is, then we need to look at is it possible to eliminate or minimize that? If it isn't, we'd implement additional measures. If it is, then we'd implement design measures or alternative modes, and we'll go through those now. So if we look at use of basic measures, we need to look at is fastenings adequate? So the fastenings shall be adequate, so they should be reliable, and the loosening of them shall require a tool. Self-loosening shall be prevented. Force opening of the interlock must lead to a reaction, i.e. damage or equivalent time-consuming measures. So it may be that there's a temporal restart. The device shall be selected in order to be able to withstand the expected forces. And what we mean by that is dynamic effects like bouncing or chattering shall be considered. So we're kind of not always careful when opening and closing guards, flaps and covers, for instance. And so the impact of that door being slammed closed needs to be taken into account, and the effect of that operation, the effect of that should not have any effect on the operation of the interlock. And we should avoid type 3 interlocking devices unless shown in a risk assessment, due to the fact that there is a lack of coding on these devices, and therefore they're easy to bypass. So now we've implemented basic measures, we need to check whether the motivation to defeat the interlocking device in a reasonable foreseeable manner still exists. And we can use clause 5.2 in 12100 for this, but we can also consider experience of use along with table H1 in the annexes of 14119, and H1 gives the most common operator tasks versus the respective benefits when defeating the interlocking device, and H2 shown here gives an example of an evaluation of motivation to defeating interlocking devices on a machine. So we need to check the extent to which the motivation can be eliminated or minimized. So we have design measures and or alternative operating modes. So the motivation to defeat can be avoided by implementing alternative modes on the operation. And if we introduce modes of operation, this can make defeating the interlock by the interlocking device unnecessary or unattractive. So by introducing permission keys, such as our pit gate and pit reader, we can restrict operating conditions to only trained, competent, and authorized personnel. So only those trained and authorized personnel can operate the interlock and stop the machine, for instance. And you may wish to run the machine at a reduced speed, so let's say during setup mode, for instance, in line with an enabling switch or a two-hand control with an encoder to determine the safe position of the speed. And you could do that if you had authorization with your RFID key. And so, you know, in the old days, you would have either bypassed the interlock by defeating it by taking it off the machine, off its bracket, or by having a spare actuator, for instance. And so, you know, this allows only trained and authorized person can operate the interlock and stop the machine. We could also use it for safe operating modes. So you could put the machine into an automatic mode. You might want to put it in a setting mode. You might want some kind of manual intervention, special or process monitoring, or just in a service mode. So it's a way of being able to minimize that at the design stage. We also need to look at with manipulation, if defeat in a reasonable manner remains, then we need to look at how can we prevent that defeat through modified or additional, if that can still happen through modified or through operational errors, how can we make it more difficult for somebody to defeat the interlocking device? And that could be by installing them out of reach. You may use a barrier or a screen, or conceal the interlocks themselves so you can't see them. And that way, you know, you're unable to attempt to defeat it. So we can prevent substitute actuation of the interlocking device, as mentioned earlier, by means of objects that are readily available, and we can use coded actuators with those. So as mentioned earlier, we have 3 levels of coding. Low-level coding covering magnetic reed switch types and reteachable RFID type interlocks. Medium covers trap key systems and limits some RFID systems, and high covering uniquely coded RFID. And for some PILT products just listed here with where we have low, medium, and high. Additional measures we can use against manipulation are caps or permanent fastenings, which we can provide for our interlocks, and we can prevent defeat via the control system by status monitoring or plausibility testing, which detects during the machine life cycle any unusual successions of state resulting in defeat. So what we mean by that is the control system expects the opening of a door in a defined machine cycle, and the absence of the control signal indicates defeat. An example may be that an actuator has been removed from the door and left in the interlock, and the door can be opened, but the interlock, and therefore the interlock is bypassed. We can also look at periodic testing. So for frequently opened guards, 14119 stipulates a test once a year for PLD and once a month for PLE rated interlocks. So therefore, the safety controller will ask the operator, we can use the clock within the controller really, to ask the operator to actuate the interlock, and failure to do so would prevent the machine from restarting. We can also look at fault exclusion, and what do we mean by fault exclusion? So the use of fault exclusion has long been covered in EN 62061, and also in a technical report 23849, and it's also covered in 13849 Part 2, and it relates to a single mechanical point of failure. In this case, for an interlock, it could be the tongue or the cam. It cannot be fault excluded to PLE by the user. The limitation to PLD for fault exclusion appears in ISO 14119, and in this example here, we have our PCEN mech interlock, which is PLC rated. The actuator is the single point of failure, which is this point here. But by using the PCEN bolt, this product here, we can claim fault exclusion as the actuator is less likely to fail due to the over dimensioning of the PCEN bolt. So we can therefore claim PLD. What we mean is that the actual bolt itself, the PCEN bolt, will take all the force and the pressures, which means that there's no stress on the actuator. So that's how we can exclude that or claim fault exclusion. To achieve PLE, especially for guard locking, the use of two devices is necessary unless the user uses a PLE certified guard locking interlock device, where the manufacturer states maximum extraction force. And in the case of PILTs, the interlocking is done via electronically via RFID in the tongue, and the solenoid is what's called a bistable pulse to lock and pulse to unlock. And we use that for our PCEN gate and M-locks. We're going to cover 13849 briefly as well, because it's not just a case of saying I need an interlock with guard locking for my machine. It's how do you determine the performance level that's required for that, and then how do you verify that as well, because you may select an interlock that's PLE rated, but depending on how you've wired it, etc., you may only achieve performance level C, for instance, for the overall safety function. So as mentioned earlier, there are two standards that can be used, 13849 and 62061, but for the purpose of this, we'll look at 13849. So this will determine what your performance levels, design. It's a hierarchical approach, so PLE would provide a greater risk reduction than PLD, and it applies to all sources of energy. It's still broken down into two parts at present. Part 1 for design and part 2 would be for validation. The process for that is a systematic approach, and we're going to look at the design really of the safety part of the control system, and how would we determine really what the performance level should be. And so in this case, we're going to use the chart out of 13849 to determine what performance level is required. So we start off with the severity of injury, which could be slight, so that's normally reversible, scratches, bruises, etc. And then we have serious, which is normally irreversible, so injury or serious injury or death. really anything that would require professional medical assistance. So, stitches, fractures, lost limbs, etc. We then have frequency of exposure, so seldom to less often, or the exposure time is short, so that's less than once every 15 minutes, or an accumulated exposure is less than 1/20th of a shift period. And F2, the frequency to continuous and or exposure time is long, so it's more than once every 15 minutes, or an accumulated exposure is more than 1/20th of a shift period. In any case, if no justification of F2 should be chosen if the frequency is higher than once per hour. And then for P, which is the possibility of avoidance, and for this purpose of this webinar, I won't be looking at the revision of 13849, which uses the table for specific conditions. But we have P1, which is possible under specific conditions, and P2, which is scarcely possible. So from that, you would determine what performance level you required from A to E. We then have our categories, diagnostics coverage, and mean time to dangerous failure that all really relate to performance level. And we can use figure 5 out of the standard. So the y-axis is the performance level, x is the category level, and the diagnostics coverage required. So they are linked. Our mean time to dangerous failure, the MTTFD, is low for green, medium being yellow, and high being red. And this chart is used, well, it's intended mainly for designers to evaluate how they could achieve a desired performance level. It's not intended in any way to verify the performance level or that performance level has been achieved. So if you wanted to achieve PLD, then you'd need a medium diagnostics coverage for Cat 2 or low for Cat 3, and this could be impacted by fault masking. It's also worth pointing out not to use the chart previously shown here for risk assessments, because we have seen that as well in the past. So categories and behavior of safety functions. So category B, safety function can be lost in the presence of a single fault. It's realized by a single channel. Category 1 is as per B, but it's less likely because we're using well-tried tested components. Again, it's single channel. Category 2 is as with 1, but it's less likely because we're using periodic testing. We're using well-tried principles. It's single channel. Category 3, we have single channel. Category 3, we have a single fault, ideally detected, won't cause loss of the safety function. The second fault can cause loss of the safety function. It is a redundant structure as well as well-tried principle, so it is dual channel. And category 4, neither single nor accumulated faults can cause loss of the safety function. Single faults must be detected, redundant structures and cross-checking, well-tried principles. So this is again a dual channel system. And then we have a way of being able to cross-reference performance levels to categories, etc. Controlling the likelihood of a loss of a safety function. So how can we do this? It's a bit like rolling a dice. Really, it's made up of many contributory factors. So it's made up of the architecture, the detection of faults to be able to react to the fault. So that's your diagnostics coverage. We have the reliability of components. We have common cause failure, systematic failures. And so diagnostics coverage really comes from functional safety standards, of which there's many. However, for this, we'll relate to 13849. Common cause failures really result from a single event where these failures are not consequences of each other. And the chance of a dangerous failure is not only based on the reliability of one component, but it depends on the total loop. So all the parameters which we design are effective on the total calculations, and it depends on the whole structure. So diagnostics coverage measures the effectiveness of diagnostics, which may be determined as a ratio between the failure rate of detected dangerous failures and the failure rates of total dangerous failures. But you have to bear in mind that diagnostics coverage can exist for a whole or parts of a safety related system. So an example, diagnostics coverage could exist for a sensor and or logic system and or final elements. And the ability of a safety function to detect itself with a dangerous failure, which would cause loss of the safety function, is expressed as a fraction or a ratio of the dangerous detected failures versus all dangerous failures. So just to run through really some Pilz guard locking products, some you'll be familiar with. So we have our PCM mech with guard locking, which pretty much covers covers, flaps, swing gates, sliding gates. We have our PCN S-lock, again for covers, flaps, swing gates, slides, sliding gates, etc. PCN M-lock, and we have our PCN S-gate. They're typically used for both are typically used for whole body access applications as well. Some new products that I mentioned for 2024 is we have the release of our S-Lock 2 and our M-Lock Mini. And so the S-Lock 2 generally used for process guarding, and our S-Lock Mini can also be used for process guarding and process guard locking too. So the PCN M-Lock Mini. So this can be used up to PLD, Cat3 applications. It's dual channel. The size is quite compact, at 30 by 30 mil by 159 high. We have our three different types of coding, which we call coded, fully coded, or uniquely coded. That means that if it's a coded type, it means that you have to use our actuator with the interlock. Albeit if the actuator was to fail, you could just buy another coded device from us and use it. If it was fully coded, then again, if the actuator was faulty, you could buy another fully coded actuator, but you can teach that up to 8 times, and then after that, both units would be defunct. Or you can have uniquely coded, which means they're sold as a pair. So if either was to fail, you'd have to order a complete M-Lock Mini again. It's a bistable power to unlock system. Again, 4 LEDs, etc., to denote the diagnostics and the status, the sizes that were ran through, and it's 60% smaller than our M-locking device. So this is just showing it here with an application on a flap cover. With different orientations depending on whether or not it's hinged, sliding. You can have different actuators. The S-Lock 2 is now it's designed up to applications up to PLE Cat 4. We have safe position monitoring with process guard locking in one. So the safety gate monitoring operation principle is a transponder technology. So that's the RFID. The guard locking operation principle is magnetic. So it's withheld via a magnetic principle. We have diagnostic functions, again, via 4 LEDs. We can use it up to IP 67. It's more suitable for food applications because there's less kind of food traps with the way that it's been designed with a single head. It comes with all OSSDs for, as discussed earlier, for series connection. We can actually now use this for safeguard locking as well. So typically you wouldn't use the M-lock in the past for safeguard locking or personnel protection because it wasn't rated if there was a failure in the magnet itself. But you can now, depending on your assessment, use it up to PLC Cat 2 applications. And then finally, based on what we've discussed today, is this a suitable interlock? I'll let you decide. So just to finish up, really, thank you for attending the first webinar of this year from PILTS. Just to run through some of the other webinars that we have this year, ranging from Pure, which is our next one. We've got safety requirements during maintenance. We're going to be looking at the right controller for application, safety and security for protection of human and machine. Understanding safety and security for protection of human and machine is what we're going to follow up with, where potentially there'll be some live demonstrations there as well, so you could ask your questions. We'll be looking at robot safety, packaging machines, and then we'll also be covering machinery safety legislation towards the end of the year. So that's what's up and coming for the rest of this year. You can also go to our PILTS Go-To Stage page to look at all previous recordings. I'd like to thank you for your time this morning. I hope you found it informative. Any questions that haven't been answered, like I say, we'll do that within the next few days. And if you've requested a copy of the slides, they'll also be sent out to you in due course. So I wish you all a good weekend. Thank you.